When we picture the ultimate goal of mining and refining, we usually imagine reaching 100% purity. We treat a flawless, isolated element pulled straight from the earth as the final objective. But if you take iron and refine it to its absolute pure state, it actually becomes a liability. Without any other elements mixed in, pure iron is incredibly soft. If it gets hot, it simply stretches and warps under physical stress. Then there's the chemical problem. When pure iron meets oxygen and moisture, it immediately begins to oxidize, flake away, and lose its structural integrity. To stop this rapid decay, early engineers tried putting a physical barrier between the metal and the air. They would paint over the iron or slather it in thick layers of oil and grease. Over time, we developed tougher physical shields. We learned how to bond a slick layer of chrome to the outside of a part, or apply chemical anodizing processes to harden the exterior. But all of these surface treatments share the same weakness. They are superficial patches. The moment that outer layer gets scratched or wears thin, the vulnerable iron underneath is exposed and immediately starts to rot. A perfectly pure metal is completely unsuited for the physical demands of human construction. It requires constant maintenance and active defense mechanisms just to survive in our atmosphere. To solve this vulnerability for steel and iron without relying on constant repainting, engineers utilize a highly specific defense mechanism called galvanization. The physical process involves taking the vulnerable iron structure and coating it entirely in a thin, tightly bonded layer of zinc. What makes galvanization so counterintuitive is how it behaves when it fails. If you physically break or crack that zinc coating, exposing the bare iron underneath to the elements, the iron still won't rust. Looking at this animated cross-section, you can see the chemical anomaly in action. Zinc is highly reactive, acting as a sacrificial barrier. Even when the armor is physically compromised, the environmental oxygen reacts chemically with the surrounding zinc rather than attacking the exposed iron. Sacrificial coatings buy us decades of structural life. But true structural perfection requires going deeper and changing the metal from the inside out. That brings us to alloying, the exact science of improving a metal's internal properties by creating a homogeneous mixture of two or more elements. The manufacturing process starts by melting the primary metal down to a liquid state. You then dissolve the secondary elements into the vat in highly specific proportions and let the entire mixture cool back to room temperature. If we look at the atomic matrix of iron, we can see exactly how this works. By introducing exactly 0.05% carbon, smaller atoms fill the empty gaps of the iron lattice, locking it into strong steel. Adding nickel and chromium creates stainless steel, altering the matrix to stop oxygen reactions, eliminating rust completely. This rule applies across the periodic table. If you want to change how a metal behaves, you mix it with a calculated dose of another substance, whether that is another metal or a non-metal. The incredible strength of our modern infrastructure does not come from finding perfect materials in the ground. It comes from deliberately engineering calculated impurities into the metal to fix its natural flaws. Industrial steel is not the only material that requires this kind of chemical intervention. The exact same rule applies to our most coveted luxury items. As this textbook excerpt clearly highlights, pure 24-karat gold is extremely soft. In its isolated, unmixed state, it is entirely unsuitable for making jewelry. A ring made of pure gold would dent, scratch, and lose its shape almost immediately. To make it wearable, jewelers must alloy the gold with harder elements, typically silver or copper. This ratio chart visualizes the Indian standard for ornaments, known as 22-karat gold. The formula calls for exactly 22 parts of pure gold mixed with 2 parts of the secondary element. That precise 2-part addition of copper or silver is in its deep yellow value and luster, while gaining the physical durability required to hold the shape of complex craftsmanship. The golden rings and chains we treasure are never truly pure in the chemical sense. They have to be masterpieces of material engineering, or they wouldn't survive being worn. Whether we are building a suspension bridge or crafting a wedding band, isolation is a vulnerability. True resilience and beauty require a mixture of elements.